Hi, myself Praful Ranjan and this is Digital Signal Processing Laboratory and experiment number 6 design of a FIR filter using Fourier transforms with window function. So we have been provided some specification for audio like sampling rate is 16 Hz and crossover frequency 2000 Hz, transition band range is 16 Hz, pass band ripple is 0.1 dB and the stop band attenuation is 50 dB. And of course filter type is FIR because we are doing FIR filter design. So determine like question is determine the following for each filter: window function, filter length, and cutoff frequency. So let's move on. What is filter? FIR filters. Like a finite impulse response, FIR filter is a filter whose impulse response is of finite duration. Like it will be not go to infinite because it settle to zero infinite time. This is in contrast to infinite impulse response filter where it may have internal feedback and may continue to respond indefinitely. So it could be like the another definition could be the output of a FIR filter depends only on the present and past input. Advantages of filter the FIR filter is that it has linear phase characteristics. This is the main concept behind the FIR filter and pass a signal without phase distortion. Also, FIR filters are easy to implement. So now let's move to the window method. What is window method? The window method consists of simply windowing a theoretical ideal filter impulse response h of n. So we will have h of n by some suitable chosen window function omega of n yielding this one. So the window method is developed to remedy the undesirable gives oscillation in the pass band and the stop band of the designed FIR filter. So we will have been given h of n and we will choose some windowing function omega of n to get the HW. So this is the theory behind the FIR windowing method. So now let's move to the types of the some windowing function. So these are the types like rectangular. The window function is one, handing is 0.5 into like this one. So in this one we will use the stop band like our given specification is a stop band attenuation is 50, so 50 dB. So we will use this one which is very near to this Hamming function. We could also use Blackman, but here we will use Hamming only. So 53. So so we can calculate the n which is given by 3.3 into delta of f, and where delta of f is equal to f stop into minus f pass and the modulus of that, and similarly fc is given is equal to f pass plus f stop divided by 2. Now let's move to the solution of the our equations like given a specification. These are the specification which we are having provided. So we can calculate the aim. So window length would be 67. I think I have missed something. Okay, yeah, it should be aim, but I used aim because sir explained as sir explained in lab classes. Okay, but now this is the so first we have to write the Hamming window function. So this is the function and this is the window length as per the explanation by the sir, and this is the cutoff frequency which could be found as 2 pi fc divided by fs, which comes pi by 4. And we already know what is high pass filter and low pass filter. So the low pass impulse response is this one. We can find by the taking inverse Fourier transform from the its response like this one, and for high pass filter it should be like this. So we can find from there. So these are the equations for h of n for low pass and high pass. So now we have to use MATLAB to design and plot the frequency response of both filter. So this is the equation. First one is h of I, which is being used for the h of I. I have written the equation from this one, and this is for low pass filter. Similarly, this one is the simple one, h n. and from that we are finding h of lp like h of the omega, which is this one. And similarly I am finding for the high pass filter, this is the high pass filter h of omega now, and here I am plotting. So plots come like this one. This is for low pass filter and this is for high pass filter, and the crossover of frequency is coming like cutoff frequencies fc is equal to like this one is 0.57 approx. This should be this. So we can find from this one, yeah, this one pi by 4, and we can observe that this is like something 1.57 divided by 2, this is pi by 4. And yeah, of course we can see in phase response for hpf and lpf that the frequencies are linearly dependent, linear. The in iir we have seen that this is like decaying like this and increasing like this, but here we can see that it is linear. Now let's move to the verification of the digital crossover design by using different music single songs. So this is the equation for I have I have made the convolution from the h of w to the x to find the y for both the low pass filter and high pass filter, and this is the results which I have got. So this is the my original signal I have taken for like 10,000 to 50,000 samples, and this is the for output for low pass filter, and this is for high pass filter. So we can clearly see the difference here. This is for low pass filter, so it is allowing only low frequencies and attenuating the high frequency. We can see this one, and output for a HP, and HP is just opposite of this one. It is allowing the high pass frequency but attenuating the low pass frequencies. So now we can what is our observation in this experiment? I observed that we can design the SP and like high pass filter and low pass filter using the window function, which we have already designed. Woofer network allows low frequency component and tutor network amplify high frequencies component. We have already seen this over. The phase response of LP and HP are linear, which is the main objective of the FIR filter. So we have seen here, these are the result for frequencies. When I pass the audio signal, the low frequency signal crosses through the LP filter and high frequency passes through the HP filter, which I have verified the method by few songs. I have taken 3 or 4 songs and I observed that the low frequencies are passing through the LP filter, and these are the and the high frequencies are passing through the HP filter. Thank you, sir.